So how would we get the volume of an irregularly shaped object, or one that has no shape? Right? So if we looked at, the jaggedy thing, we could probably go through and say, well, there's some triangles and then an oval. We could pull out the mathematics on how we determine the volume of a triangle, how we determine the volume of an oval. We might be able to come up with that one. But the shape of a three-dimensional crown, that's going to be hard to do. And the shape of the last one, it's really hard to get a picture of this, by the way. What is that supposed to be a picture of? Let's not worry about the bowl so much. What are we trying to get the volume of? A gas. Yeah. It's going to be really hard to get the volume of a gas because that fills whatever object you're in. So how could we determine what? It's art. How would you determine the volume of those objects?
Place them in water.
Okay, so what we can do is take advantage of displacement. So what we could do is put them in a graduated cylinder or some other device that measures volume. And when we place the object in there, it's going to displace the amount of water equivalent to the volume. Right? So what's written in underneath this is unfortunate for whatever reason. Right? Was it Archimedes? I think gets credit for it. Is it Archimedes for volume? Eureka? I think it's Archimedes. He sat in a tub because he was challenged with trying to find out if the crown was actually made of gold. Right? And the only way you could do that is by using density. So how does he get the density? Couldn't figure out how to get the volume of the crown until he sat in the tub and noticed the water flow out of the tub. It was like, oh, eureka, I can get the volume of the object by measuring the water that it displaces. Once he has the volume, you can then calculate the density and do that for standard gold, and you can identify that the crown is made of gold. Okay? So we can use that to our advantage to come up with volumes for things that we can't really get a hold of easily. Right? We can do it with gases as well. Okay? So we could take a reaction container, and so what this is attempting to show is that if we have something happening in that tube, we add a little bit of heat to it, that reaction produces a gas. Where does that gas go? Well, that's going to go up this tube and then down here, which is now going to build up pressure above the liquid. That pressure will push down on the liquid till eventually what happens?
It flows back out.
Liquid rises up this tube and collects in a secondary container. So if I know gradations on that secondary container, I can determine the volume of gas produced. There's a bit of a problem with this experiment. Right? Has anybody taken a balloon and heated it up? Yeah, what happens to the balloon?
Shrivels up first. What's happening? Is there helium in there?
Any balloon, when you heat it up, what happens? Before it pops, it starts to expand. Okay? Gases have some interesting properties, which we'll talk about later in the semester. Okay? This is why we have hot air balloons, right? What happens when you heat up the air in that balloon? It expands. Okay? We have the deflated balloon that now fills with air. Okay? It's filling with air, and then we get a rising effect, which is another secondary thing. But it expands. If I now put heat behind what is effectively a balloon, what's going to happen to the gas? It's going to expand, causing water to move out. Is it because I've produced gas, or is it because I've added heat to the reaction? I don't really know. It could be a contribution from both. It could be because the gas is now hot and moving more, or it could be due to the presence of more gas particles. Okay? So this experimental design is a little bit iffy. If we were to fix this, what we could do is just say that the gas comes out and then travels this big long tube before coming back in. What's happening in that big long tube thing? It's cooling down. So that way the only transition for the volume change is now due just to increased amount of gas particles, not due to temperature. Okay, so you would want to separate the heat from your measurement by as much as possible to minimize the effective heat affecting your results. Okay? But it does work as long as we take that into consideration, and we could monitor the volume of a gas this way. Okay? Once we have volume, we can go through and come up with density. Okay? And density is now an intrinsic property or a physical property. Okay? And the fun thing that usually comes out of this is which weighs more, a pound of lead or a pound of feathers. And dang, I forgot the video. Which weighs more? They weigh the same. They're both a pound. Okay? There is no difference between them. Okay? Well, the pound of feathers, there's an internet meme, right? The pound of feathers weighs more because you have to live with all the death of all those ducks to make those feathers. Yeah. Okay? That's a secondary issue, right? So when we're asking that question, it's usually a question we like to ask little kids or people that don't quite see that parallel, because we almost always go, well, lead. Okay? And really what our mind is thinking is, it turns out it's a massive psychological question, believe it or not, is that what we're really interpreting in that weight is which one would I rather be hit by? Right? Would you rather be hit by a pound of feathers or a pound of lead? Why would you be rather hit by a pound of feathers than a pound of lead? Okay? It's not even really cushion. Where's that pound of feathers? It's spread across a much larger area, whereas the lead is now in a tiny little ball. So that pound of lead is now going to impact in a very small space. Okay? So when we think about that question, we tend to ignore the mass, and really what we're probably doing is comparing actually out the density or other aspects, but density is probably one of the larger contributors there. And so what we're missing is the relationship between mass and volume. That is density. Okay? So mass over volume is defined as your density. How do you determine a mass?
Balance.
A balance. You weigh it. How do you determine the volume? Displacement, if it's an irregularly shaped object, or we can do length times height measurements for a nice normal shaped object. But ultimately what we're looking at is now the relationship between mass and volume. What is density? You've got one really easy answer that I'll accept. If you don't give it, I'll give it to you.
Mass over volume.
It's mass over volume. Right? Yes, density is mass over volume. Good, simple answer. Why? What is the point of doing mass over volume?
Get the density.
How
No,
heavy
not quite.
it is based on the amount of space it takes up.
Why is that important? What am I using density for?
Finding a substance. That's where it is.
We could use it to identify a substance. That's now looking at density. I don't care about mass over volume. Why do I care about mass over volume? That's looking at the concept of density. Why do I care about mass over volume?
If someone says you have the choice between getting hit with a pound of feathers and
So we could try and go back to what I suggested at the beginning. Okay? If I'm going 15 miles an hour and I'm trying to go to LA, is that a good idea? No, why not? Okay. What's the issue with that? What's wrong with going 15 miles an hour on the way to LA? It's going to take a really long time to get there. How do you know it's taking a really long time to get there? What did you do?
The speed and how far away.
What you've done, because you have a concept of those units, is that we said the time to get to LA, okay? And we said 15 miles per hour, right? So hour, 15 miles, 1 hour, and you know that the distance to get to LA is a lot, okay? 500-ish miles, which would say we're doing a really long time if I'm going 15 miles per hour. You've internalized some of that calculation to get a ballpark estimate. What was miles per hour for you? What did miles per hour do for you? Showed you how fast you were going. Why did you need that? What did you use miles per hour to do?
Estimate how long it would take to get there.
So for instance, if I get rid of miles per hour, can you solve this? No, you would have no idea how long it takes to get to LA. What is miles per hour? I think I just heard you mumble it over there.
Is that really the right answer, the density?
No, it's not a density.
That's the actual miles per hour.
What is miles per hour?
Measurement?
A unit. It's not a measurement. Okay, if anything, miles per hour is two measurements. I have a measurement of length and time. What is miles per hour? What does it allow me to do? Miles to time. What am I doing saying miles equals to time?
You're converting.
I'm converting. What is miles per hour? It's a conversion factor. What is density? A conversion factor. Right? That's all it is. The entire unit of chapter 2 is just conversion factors. Density just happens to be a chemistry conversion factor that allows me to convert mass into volume, or volume into mass, depending on what I'm looking at. Right? So anytime we see a complex unit where we have one measurement over another measurement, we have a conversion factor. That conversion factor allows me to now do dimensional analysis. Okay? Units for density. Right? So we just said mass over volume. Well, what would be a unit for mass? Grams. What would be a unit for volume? Milliliters. Why would we pick grams and milliliters? When you go to weigh something in the lab, what was your mass typically? Usually in the gram scale, right? Okay. What is your volume typically? Milliliters. Okay. Why do we pick grams and milliliters? Because when we weigh things out, or we determine volumes, the volumes we're working with, the grams that we're, or the mass that we're working with, happen to be on the scale of grams and milliliters. When I look at solids, they typically are represented in grams to milliliters. Does that say milliliters? It says centimeters cubed. What is centimeters cubed? It's equal to milliliters. It's the same unit. For liquids, we'll notice we get the same unit system. Grams and centimeters cubed. Okay? Or milliliters. What do you think about water vapor? Do you think it makes sense to look at gas in that same unit? No, why not? Yeah, we could still weigh it. If I was to draw a shape for ice, so here's the shape of a single atom of ice. I'm getting at the right idea. If we looked at ice, right? That's ice, right? Virtually no space in between them. What would liquid look like? A little bit more space. Okay, probably not that much more, but a little bit more space. What happens when we move to a gas? Tons of space. Those particles are now insanely far away from each other. Okay? Which means for that given volume, what would be the mass of gas in that box?
Very low.
It would be very low. The number ends up dropping so low that we'd be using lots of decimal places. 0.0001, let's say, grams. Okay? For water, that was awesome. It was 1, nice and easy. For ice, it was 0.917. Okay? Effectively, 1. So we could deal with that. 0.0001. Is that the same thing as 1? Okay, well, I could make it look kind of like 1 by doing what? Scientific notation, which it would be 1 times 10 to the, not fourth, negative fourth. How many of you like powers of 10? How many of you like negative powers of 10? Oh, fascinating. Most people don't like dealing with units or numbers that are so small or, for that matter, so large. So what do we do to help our human brains wrap around that concept? We change the unit system. Instead of looking at grams per milliliter, I could look at grams per cubic centimeters, the same thing as a milliliter. I could expand the volume out now to a liter. If I make it a larger volume, that could incorporate all of that mass, making this number get larger. Or instead of going grams, I could have used micrograms or milligrams. So I could change the unit system when I go through to represent those different phases. So when you look up densities for solids and liquids, they tend to be in grams per milliliter. Gases, the unit system changes because the numbers are so small if we use that same unit system that we want to change it to make it easier to manipulate. Okay? So if we take a look at some densities, for solids, what's our unit system? Grams per milliliter. For liquids, grams per milliliter. Those densities are all about the same. When I move to gases, what happens to my unit? Grams per liter. If we look, the numbers don't look all that different across the board. But because the unit system changed, that's a pretty big difference. Does that make sense? Okay, so we have to recognize that numbers aren't absolutes. We also have to take into consideration the units behind those numbers. Make sense? Okay. How could we apply density information? Well, I've got a cylinder here with 3 liquids in it and 3 solids. Right? Why is the purple solid all the way at the bottom? It's density. The purple solid has the highest density of all of those substances, which means what does it do? It sinks to the bottom. What about the orange solid or red solid, depending on what color you see? It's less dense. Less dense than what? Okay. Our red one is sorry, say that again.
More dense than L1, less dense than water.
Okay, it is more dense than L1. Why is it more dense? Because it's at the bottom of L1. But it's on top of water, which means it's less dense than water. So we can use the densities to help sort things out. Everybody's saying, well, that's kind of bizarre. I would never use this in the real world. Turn 21 and go order fancy drinks. Okay? You see that density is used in those cases because that's largely how we get fancy, colorful drinks, is based off of density differences of the varying either artificial sweeteners or alcohols. Okay? At very least, order them and make somebody else drink them because then you can at least see the cool stuff. Okay? Makes sense? But be 21 first. Okay? Back to the point of density. Density is a conversion factor. Okay? So if I'm given this question, what is the density of a platinum nugget that has a mass of 224.50 grams and a volume of 10.0 centimeters cubed? Okay? If we left it at that, whoops, that would be a really potentially difficult question to answer. Why would that be a difficult question to answer? What is density? Okay. So to answer that question, what did you memorize? You didn't memorize a conversion factor per se. What did you memorize? That density is mass over volume. You're not memorizing a conversion factor. What are you memorizing? The chemical equation that density is mass over volume. It's a chemical equation you've memorized. Okay? Well, what density do I want? correct one. I want the density of the nugget. I can accept that. Okay. Do I want the mass in milligrams? And the volume in decaliters or deciliters? No? Why not?
Because doesn't look good. I like grams over centimeters.
It's the wrong units. What do you mean it's the wrong units? What units were asked for? What are the units that are asked for? Does it ask for the density in grams per centimeter cubed, by the way? No, it doesn't. Right? Unfortunately, we will ask questions like this. I try to watch out for it and avoid this kind of system. Okay? What you could do if you saw a question like this would be to look at your multiple choice answers. And what would you hope to see in your multiple choice answers? A number, whatever that number is, followed by grams per milliliter. What unit are you being expected to find? Grams per milliliter. So you could use your answer choices to help key in for what unit system you're expected to use. Right? How else could you look for that information? Oh, who's at the door? If we read the question a little bit more carefully, it actually says grams per centimeter cubed. How did you guys miss that? It's right there. It was a joke, for those who didn't get it. I erased it, and I just unerased it. There it is. Right? So with that information, we could now go through and solve the question. Right? With that information, I would also argue that what you memorized, that density equals mass over volume, is also now unnecessary. You didn't have to memorize that formula. Why not? You're being asked to say what the density is. I don't know the formula for density. Am I told what units I'm supposed to get to? Yeah. I want what? Grams over centimeter cubed. Am I given grams in my given information?
Yep.
Yeah, where does that gram unit need to show up? In the numerator. So 224.50 grams. What do I want to put that over? Right. This is where we can have a little bit of kind of debate on this. I would argue you would put it over 1. Right? I don't want to put it over anything. So if I put it over anything, I'm saying the given information was 224.50 grams over something. Is that what that given information says? No. It just says 224.50 grams. Okay? Grams, I placed it in the numerator. Why did I want the gram value in the numerator? Because when I look at the goal, where I started this whole process, where was the gram unit written? In the top, on the numerator. That's why I'm placing that gram given information in the numerator. Are my left and right equal? No, so what do I need to do?
Times 1 over 10.07.
Times something else. What should be at something else? Well, grams I already have figured out. What am I missing? Centimeters cubed. So I want to put centimeters cubed right there. Okay. Am I given information about centimeters cubed? Yes, it says 10.0 centimeters cubed. Where should the 10 go? Next to centimeters cubed, not in the denominator. Okay? Because if you go through and start to memorize, oh, things go in the denominator or numerator, when they swap, they're going to go to the wrong spot. Tie them to the unit. Notice, what did I write first? Centimeters cubed. 10.0 centimeters cubed. What goes in the numerator? 1. Right? All I'm given is 10.0 centimeters cubed. I know that number needs to show up in the denominator. The stuff that shows up on top is now nothing. What happens if I run the calculation? What unit would I end with? Grams per centimeter cubed. Is that what I want? Yeah. So now I can enter it in a calculator and do it. For those of you that went through and said, well, isn't what you wrote exactly the same as saying this? Right? Isn't it exactly the same?
You just skip a step.
Okay. What's shown in black is a formula that you memorized. If you want to go through and memorize formulas, that's on you. You can go through and do that. The problem with that is you now have to memorize stuff. How many people in this classroom are like, yay, memorization? Okay. Interesting. So don't tell me you want to do this, because you don't. Okay? We want the process behind it. Okay? If you go through a physics class and you look at mechanics, you've got time and velocities, acceleration, all these formulas they throw at you. Guess what all of those formulas are? Conversion factors. There isn't a single formula you have to memorize if you apply your conversion factors. You have to go through and evaluate, how do I relate those conversion factors? That's the power of conversion factors. Okay? No more memorization of formulas. Kind of, sort of?
One thing to think about is, this came up in my math LC the other day, when we're looking at this, it's also a consideration of visual design. Some people might see these two things as synonyms because you can simplify one to the other, but when we split it apart like this, we're saying that we have a different purpose and we're using our visual design to emphasize key pieces of information. By splitting it up the way Mike does, he's telling you a new process and saying that there's a reason he does that. It's to make calculations when things get more complex, simpler. So we are using visual design here to not just represent the formula, but we're intentionally changing it or representing information in a different way so that we can process that information more accurately or in a different way. Does that make sense? So it's a writing visual design component is all I'm trying to say, or consideration.
Does that kind of make sense? Right. And it is a challenging concept. Almost everybody wants to jump once written in black. You don't lose points for that. Okay? I might just put an unhappy face next to it, but that would be it. What you've done is technically correct, but you've memorized when you didn't have to. Okay? So, your turn. Solve for it again, except this time I want the density in pounds per liter. If you got questions, feel free to raise your hand. Okay? Work it out. Set up the work, the calculations to run through this conversion factor. So let's start out the process. Step 1 of our process is what? Dance, sure. What is step 1 of our process? No. Write out what we want. What is our goal? Where are we trying to get to? If I don't know the goal, I can't start. Right? So what am I trying to get to? Pounds over liters. Okay? Now that I know my goal, I can start to incorporate given information. What do I want to start with?
Let's go.
224.50 grams is a perfectly acceptable place to start with. I'm going to challenge that I have no idea why you're starting with that.
Oh, I never got the answer anyway, so.
Okay. Well, that could be why. Why would you start with 224.50 grams? Because what? Grams is the same thing as pounds? No, so I don't accept that. What are you pointing at?
I was pointing at the pounds
I would argue dealing with 1 pound equals 454 grams is probably a better place to start. Why is that a better place to start? Right there isn't a bad answer, except I could just as easily say 224.50 grams is right there too. Still not quite right. What am I trying to get to? Pounds, right? I want pounds in the numerator. Does 224.50 grams say anything about pounds? No. So why would I start with that? It doesn't have anything for my target. Okay? So it could be useful, but I don't have any logic or reason behind why I want to use that. At least not in its obvious format. So I would make the argument that this pounds equals 454 grams is more relevant to use. In that argument, I would say that I want pounds in the numerator. Why? When I look at my answer, pounds is in the numerator. Those pounds are being directly related to grams, so I can't remove that gram value. It's now tied to it. Okay. What number shows up with pounds? 1. How do I know it's 1? You literally look at your conversion factor, and what number shows up in front of pounds? 1. What number shows up in front of grams? 454. So this is a phenomenal first step, because what do we now have? Pounds in the numerator, and what do I want in my answer? Pounds in the numerator. So this is great. This is fantastic. I'm working towards an answer. But at the same time, what have I screwed up? I have grams in the denominator. Do I want grams in my answer? No. So what has to happen in this next step? I want to cancel that gram value. Okay? So I'm going to put grams here. Ideally, I go back to my question, and what do I find? Just grams. Okay? I don't want to convert to anything else, because if I convert to anything else, I'm introducing a new unit. So I don't want that. All I want is grams. So I go back to my question, and I say, please give me grams. Is it there? Yeah. We have the information that 224.50 grams was given. So I can now go in and write 224.50 in front of grams. Why do I not place it in the denominator? Because where's my gram unit written? In the numerator. The number in my given information is close to grams, located where? In the numerator, which means numerator. What shows up underneath it? 1 should show up underneath it. Okay, why? If we ignore all other information, what shows up underneath that measurement? Nothing. Okay? Which means when I go through to enter it into my formula, I don't want to put anything there. Okay? Would this now be my answer? No, why not? Because if I look at this, I get grams cancel, and I'd have pounds. I have pounds in the numerator. I have pounds in the numerator in my answer. Isn't that my answer? What's wrong with it? I need liters. Where do I need liters? On the bottom. So I'm setting up another conversion or another calculation. That calculation is independent of the other one. And in that, what do I want in the denominator? Liters. All right, what do I want in the numerator? There's no reason to put milliliters yet. What do I want in the numerator? Rhymes with something. I'll accept 1. Okay, nothing. All I want is liters. I just want to be able to put the number in and calculate. I don't want to do anything else. Am I given just liters? No. So I'm going to have to convert those liters to something else. What do I choose to convert those liters to? Okay. Well, is there a volume measurement given to me? Yeah. What volume measurement is given to me? Centimeters cubed. How many people memorized that conversion factor? Oh well, that conversion factor doesn't exist. So I can't convert to centimeters cubed. What am I going to try and convert to? Why did I pick milliliters and not say something else? Decaliters, deciliters, hectoliters. Why am I converting to milliliters? We could run, it's the most common measurement for densities, so it makes sense to use liters. Another option, look at some of the given information. What do you see? Milliliters is given information. Maybe milliliters is useful. Do I know how to convert liters to milliliters? Yes, because I was told to memorize by Mike that milli meant means 10 to the negative 3. Where does the power of 10 always go? With the core or root unit. What is our core unit? Liters or milliliters? Liters. 10 to the negative 3, 1. Okay. Phenomenal. I've now brought in the liters unit. So I would have pounds per liter. No, why not? I still have milliliters there. I need to get rid of the milliliters. So I'm doing another conversion factor. And in that conversion, I want milliliters to show up on the denominator. Why the denominator? So the units can cancel. Okay, so I would go back to my question, what do I hope to find? Just milliliters. That is again my goal. I want just a milliliter value. If I'm given just a milliliter value, all I got to do is plug it in and I'm done. Am I given a milliliter value? No. So what does that mean I have to do? A conversion. What am I going to convert milliliters to? Centimeters cubed. Why did you decide to go to centimeters cubed? Because there was a conversion factor given there. Okay, so maybe it makes sense to use it. Right? If you look at the front of your exam, you have a bunch of conversion factors. Just because it's there isn't a good reason for it. What you might be doing is propagating this out just a little bit further and realizing that now I'd want to get rid of centimeters cubed. Am I given just centimeters cubed in the question? Yes. So I'm kind of playing a game of chess. I know where the end goal is. I know what pieces I need to use. How do I set it up so that I can use those appropriately? What is the conversion factor between centimeters cubed and milliliters? 1 centimeter cubed is 1 milliliter. How many centimeters cubed should I be putting down here? 10.0. What shows up in the denominator? Sorry, the other place, the numerator. 1. Because again, there's nothing else associated with that measurement. What happens when we run our calculation? Centimeters cubed cancels, milliliters cancel, and what will we have? Pounds over liters. We could now go through and enter this into the calculator. Okay? We're really going to have 2 people in this class, or 2 categories. One category of people that thinks this is really, really hard, okay, but they're struggling through to get this right. You're in an awesome place. The other category that says this is really, really stupid to show all this because I can do this in my head. You're going to have a horrible time in the next unit. Okay? Because you won't be able to do these individual conversion factors. The placement of those numbers comes solely down to knowing what unit they're tied to. If you don't understand why the units are placed in their individual locations, you can't place the numbers correctly and you'll end up getting the wrong answer. For those of you saying, well, but that's not going to be a big deal, it will be, because what I will go through and do for multiple choice is put in every permutation as possible multiple choice answers for which way you dropped those numbers in. which means if you have some idea that you just need to multiply and divide somehow through here, and you just start punching in random things, guess what? That answer choice is one of your answers. Okay? You have to know why you place the numbers where you do to make sure you enter it into the calculator correctly.
And keep in mind what we learned about writing technologies and why they exist. Your brain has a limited amount of space and ability to cognitively function. So the more complex the problem gets, the harder it is for your brain to hold all that information, which is why people use writing in the first place.
Okay. The whole point is this process to simplify your calculations. Okay? What we're trying to set you up for right now with these conversions is not to do these conversions. That is not the goal. The goal right now is to pick up a process that you can trust and move forward into the next unit where you won't be able to trust those units or those numbers. Yes?
Is there possibly multiple ways to set that up, or is that the only correct way? Because I did it differently.
What do you mean? How did you do it differently?
I started with the grams that were given, and I did 224.5 grams over 1. And I did times, because the way I go through it is I look at the
Keep going.
pounds first. So then I did times 1 pound over 454 grams. And I did times 1 over 10.0 centimeters. And then I kind of cheated a little bit because I had the exam out, and on the exam it gives you 1,000 centimeters cubed over a liter. So then I just went to 1,000 centimeters cubed over a liter, and then I got my answer there.
Are these two methods different?
I mean, do they get you the same? I think they get you the same answer.
I didn't ask if they got you the same answer. Are they different? No. There's absolutely no difference between them. They do the exact same thing. It's just a question of what logic did you use to pull things in. Right? And the question that I'm going to ask is right here at the very beginning. Why did you use 224.50 grams?
Honestly, why is because of the way that I do it, because I don't look.
And that's fine. We're trying to get at a conscious decision here. This is good.
I was looking at, because I know you have to have pounds on top, so I was just looking at what you're given first, kind of thing.
So, with given first, that is usually a standard strategy for solving these things. Okay? If you take a look at the short answer on the practice exam, the second page of the short answers, CD. Nearly everybody goes through and solves that with the first piece of given information, and you solve it wrong. Just because it shows up first does not mean it's right to use. Okay? So you can still use it, and that's where things become questionable, is you have to be careful that your process shows those units appropriately. And if you use the given information incorrectly, because you don't have a solid reason for why it's being used, you get the answer wrong. Okay? So
choosing the given first is okay as long as you're being careful as you do it.
choosing the given first is only okay if you know why it should be used first. If you're choosing it first because it's first, you're wrong. Okay? Will you still get the answer right 50% of the time? Probably. Is that an acceptable grade for you on the exam? Okay. So you need a better reason than it's first. Okay? And I would argue there's absolutely a solid reason why you can use 224.50 first. But you need to have that reason. What is that reason? What is the formula for solving density? Mass over volume. What is grams? Mass. I memorized the formula. I know I need to start with mass first. Perfectly acceptable. You had to memorize stuff. That's fine. There's another reason you can do it without memorizing the formula. What is pounds a measure of? Mass. Where's my mass measurement show up? In the top. Where's my mass measurement going to need to show up? On the top. Okay? If you have made that conscious understanding for why you're using that, you're fine. If you aren't consciously making that decision, you're now in a 50-50 split. Half the time you'll be right, half the time you'll be wrong. Right? If you follow the process honestly, you'll see that you're wrong and can very quickly fix it. Right? If you don't follow the process, you'll just fudge it and get it wrong. Right? And whatever it was, D in the practice exam is a classic example of that. Okay? Roughly half of the class on that exam got that question right. Right? And it's all because they used the wrong thing first. We have to acknowledge why we choose the things that we choose when we go through to solve. Right? Yes?
So like on the last piece of the one that Molly did, where
Uh-huh.
it's centimeters cubed to liters,
Uh-huh.
if we put something like that, we don't break it down into like milliliters and do another conversion, would we get points wrong?
Nope. As long as that conversion factor is a true conversion factor, I can't take off points. If you decide to memorize all the conversion factors, more power to you. Okay? Absolutely fair game. You can do whatever you want. Okay? If, however, one of those is wrong, okay, that's where you then run into a problem. Okay? And in this case, you would run into a problem because what I was expecting was multiple conversion steps. You're now, if you screwed that one up, you're now missing both those conversion steps. That's now a big loss of points. You tried to condense two conversions when you didn't need to, and you screwed it up. You're doubly screwed.
Yeah.
Okay?
Because they did it that way, but it was just
Mhm.
actually.
Yep. So that's where you have to be careful with your conversions. You're allowed to use other ones as long as they're true. When they aren't true, becomes the problem. Okay? One of the things that's nice with our conversion factors is the order doesn't matter. This is all multiplication division, meaning it is communicative, which means we can start wherever we want. The question again is, why do you start? Okay? What is the reason behind your starting point? If you don't have a reason for that starting point, you're getting lucky by guessing. Okay? Which is, again, also fine. Just realize that's what's happening. Okay?
So for like this question on the practice,
For the practice exam, I'm going to say you can talk to me after class.
but wait, but
Oh,
this
yes.
involves like the exam as a whole. If we don't go about doing it and setting it up like that, and we go through it, solve it a different way, but get the right answer, do we get points marked off?
As long as all of your conversion works are shown, you're fine.
What if we don't set it up explicitly like
If you just give me numbers, you haven't shown me how to convert units, and it's wrong.
What if we do it in like pieces?
So that's another option. If we look at each of these, those are multiple conversion steps. You can go through and individually set up each of those conversions as ratios. I'm fine with that. For that question, you're looking at 3 different equations. 3 different equations means 3 different opportunities to screw up your calculation. That's why the single line method is better. Okay? You absolutely must show units. You could screw up your numbers up the yin-yang, but if you show me the units, you'll get more points because you're acknowledging how and why those things are supposed to happen. Okay? And again, it's not for this, it's for the next section. That's the whole point of doing conversions. I don't care about conversions now, I care about the process. If you don't have a process, I'm going to subtract points.
What's the next section then?
The next section is units looking at chemical reactions. So now what we'll do is take all of the conversion stuff that was independent of reactions, and we'll take reactions and conversions and we'll smash them together into one thing. So everything that you did in chemical equations and everything we do in conversions is now one giant mess of an equation.
And the numbers get more complex.
And the conversion factors become significantly more complex. Okay? Again, with our puny brains not being able to deal with it well. Okay? Ignore that. So, conversion factors. Okay? How many meeks are in 3.4 steps? What? I don't know what any of those units are. This kind of question is exactly what trips people up in this section. Because you go, oh, I can't do that. I don't know how to solve that. We could throw in a little bit more information. 1 meek is 4.5 times 10 to the 3rd steps. Well, should I multiply? Should I divide? I don't know what's going on. The only reason you don't know what's going on is because you don't have a process, right? Your process that you've been, oh, no, this works, I don't need to do all this fancy stuff, is because you've already memorized an algorithm to solve those questions. If we shift it to a system that is no longer algorithmic because it doesn't match your current understanding, you're dead in the water. Okay? Kind of makes sense? So, process. Double replacement reactions. You are required to predict these. So we could go through and come up with our products. How do we know that barium chromate is BaCrO4? How do I know that to be true?
Because we know barium and then we know chromate.
We know what about barium?
That it's Ba.
Not quite. Said another way, how do I know this isn't Ba2CrO4? Barium is a +2, chromate is a -2. How do you know barium's a +2? Periodic table. How do you know chromate's a -2? Is chromate one I told you to memorize? No. How do you figure it out? You look at the other side of the equation. Are you required to know that potassium's a +1? Yes. If you have 2 potassiums, what is the charge on chromate? -2. You are still expected to know that that is a proper formula for barium chromate, even though you aren't required to memorize the charge on chromate. Okay? The rest of the equation can give you that content. How do I know potassium chloride is KCl and not say K2Cl2? Because I mean, there's 2 potassiums over there, there's 2 chlorides over there. Right? Why is this not K2Cl2? What does the red 2 for potassium mean? That there are 2 potassiums. Why are there 2 potassiums? To balance chromate. When I move over to potassium chloride, is potassium with chromate anymore? No. So the 2 was there, so I balanced chromate. Is chromate? No. So what should happen to the 2? It shouldn't be there. Why is there a 2 with the chloride? To balance barium. Is chloride with barium anymore? No. So get rid of it. Okay? Is the equation balanced? No. Once you have the proper products, now you could balance the equation. And notice that, yes, so I have 2 chlorides, 2 potassiums, and I don't have 2 potassiums, 2 chlorides on the other side. How do I fix it? I put a 2 in front of the potassium chloride. Now I have 2 potassiums and 2 chlorides. Now the equation is balanced. What is the sum of the coefficients of this balanced equation? What are the coefficients? In general, define coefficients. It is the number in front. What is the number in front of barium chloride? 1. Why is it a 1, not 0? If I had a 0, then that would say there isn't barium chloride. Why did I write barium chloride? It's an implied 1, 1, 1, and 2. The sum of the coefficients is 5. Okay? I could do the same thing for the bottom one. Anybody notice anything interesting about these 2 equations? Or different? Both of them involve the alkali metals. One is a chemical reaction, the other one is not. How do I know that? Chemical reactions we know to be chemical reactions because of change in phase, change in temperature, change in color. Can we look at a change in temperature? No. Can we look at a change in color? No. Could we look at a change in phase? Yes. The phase information is specified after our formula. Note that we started with 2 aqueous systems and we made a solid. Did I change phase? Yes. The bottom one. I started with 2 aqueous and I end with to aqueous. Did I change phase? No. The bottom one is not a chemical reaction. The top one is. How would I know what the phase was? I have to reference a solubility rules table. The solubility rules are given to you as a shortened form on your exam. Okay, you are responsible for being able to interpret that. So use it on your practice exam to make sure you know what it means. Okay? If we go through and evaluate this, let's take a look at the barium chromate. I need to find barium or chromate in this list. Okay, in rule 7, I see chromate. Okay, it just says chromate, and then it's got a parenthetical. What is the title of that section? It says ionic compounds containing the following are generally insoluble. If they're insoluble, they don't dissolve, making them solids. Chromate is insoluble except for rule 1. What was rule 1? Are alkali metals. Is barium an alkali metal? Barium is an alkaline earth metal, not an alkali metal, so it doesn't match the exception. It is now insoluble. There's the solid. If we take a look at the reactant with our chromate, okay, where is potassium? It is a group 1 metal, which means it is an exception to always insoluble. The exception to insoluble would be soluble. The phase must be aqueous. Right? So you have to use the solubility rules to be able to interpret these equations. Okay? Neutralization reactions, you're identifying an acid and a base and mixing them together to produce a product. If we look at the complete neutralization for this, it becomes a tricky one because you got to do nomenclature. Sulfuric acid. How do we know it's a ternary acid? What about sulfuric acid says 3 or more atoms? We know sulfuric acid is a ternary acid because it does not use the word or the prefix hydro. With the prefix hydro, I would know it's a binary acid. Without the prefix hydro, I know I'm looking at a ternary acid. How do I know it's SO4 and not SO3? It's sulfuric acid. I ate too much, so I got sick. It's sulfate. How do I know I need 2 hydrogens? Because the charge on sulfate is a -2. Charge on hydrogen? +1. I need 2 hydrogens to balance it. Okay? If I'm now to predict this reaction, it is a double replacement. It is a tricky double replacement, but what we're looking at exchanging is the metal potassium as a +1 with the non-metal but acts like a metal hydrogen +1. The result becomes HOH plus KSO4. Is HOH a proper formula? What is the charge on hydrogen? A +1. What is the charge on hydroxide? -1. Do I have a proper formula? Yes. I could also write that as H2O. I would make the argument that HOH, particularly color-coded, is a little bit more helpful. How about potassium sulfate? Charge on potassium, I already started to hear someone say it. A +1, the charge on sulfate, a -2. Is that formula correct? What do I need? 2 potassiums. Now I could go through to balance the equation. Okay. That will balance it. Am I expected to predict phases for these? Neutralizations are a type of double replacement. Are you expected to predict phases for double replacements? Yes, which means neutralizations? Yes. Potassium sulfate. Potassium is a group 1 metal, making that species. Aqueous. H2O or HOH, that might be a hard one. That's not going to fit under my solubility rules. All right, what phase is that then? It's a liquid. How do I know it's a liquid? Because it's water. That's how we know it's a liquid. You're supposed to know that. Okay? You may not acknowledge it beforehand, but now you know H2O, liquid. You should write that. Does it make sense to reference it as aqueous? Because what does aqueous mean? Aqueous means soluble in water. Is water wet? Use the internet. Use the internet. No. Water is not wet. Combustion, your combustion reactions are a reaction of an organic material, typically carbon and hydrogen, with oxygen gas to produce carbon dioxide and water. Okay? This was a really hard one to balance, which I believe we already looked at, so we won't stress about it. But what you acknowledge or need to be able to do is, number one, predict products for combustion. What will the products always be?
Gases.
Carbon dioxide and water. They're always those products. So when I write the equation, I say, what will they always be?
Gas and carbon dioxide.
You look at the reaction where they were given, because it's always that. Okay? We won't worry about temperature. It won't be on the exam, and we'll pick up with temperature after the exam next week. It'll be exciting.